The problem is, given a x, we want to find y, we satisfy this. And if you know the initial condition like y naught, so y naught is a number, y naught is a number, x naught also a number. Okay, so y at x naught the value is known to you. So let us call this column 1. Okay, so our objective is find a function y which satisfies these two problems. This is also there, correct? These two. So of course, first question we have, what is the guarantee that this problem has a unique solution? What is the guarantee this problem has a unique solution? So we have several theorems such that this problem has a unique solution. But I will skip because you are not aware of Lipschitz continuity. Do you know Lipschitz continuity? No. Okay. But this I have mentioned in my slides. So how do I find a solution? For example, suppose you have a simple column dy by dx equal to y and y is 0 equal to 1. Can you tell me what its solution is? Quickly. Can you tell me what the solution is? What is my y is? Yes. So you are looking for a y, correct, which satisfies these two equations simultaneously. So can you tell me the solution now? Do it. dy by dx equal to y0 equal to 1. What is the solution? Any idea? So it means you are looking for a function y. If you differentiate this, if you differentiate function, you get that function y. Correct? So what is the answer? Have you seen differentiation before? Yes? Now you know how to solve this, correct? So answer is y is equal to exponential x. Correct? Or this is you write exponential, correct? This is your answer is. It must satisfy both the condition. Both first and second. It is clear? Then this is the. But our problem is sometimes this function, let me take this like very bad function, very bad. And why this f of x y is a very bad or very crazy function, so that you cannot integrate or you cannot. Then how do I find the solution? So we have to go with numerical solution. So first we need to understand what do you mean a numerical solution. If we understand, then how do we find it? Understand? What do you mean by a numerical solution? And the next would be, we have how do we. So I assume that this my assumption is one has a unique solution. Unique. Then only we can find. First, this must have a unique solution. So I assume that this will have a unique solution. Then how do you find the unique solution? Correct? Is this clear? If you want to be more precise, so x actually belongs to some interval AB, which is given to you, and this x naught is any point of this interval. It is not necessary that x naught has to be A. This is what we feel. Sometimes the x naught has to be A. Initial point. It can be any point of that interval. So this x naught can be any point of this interval. That's the point. Okay? Can be any point of the interval. Is clear? Problem is? So assume that one has a unique solution, then how do we find it? How do we find it? Okay, that's it. Idea is, so let us rewrite this problem. See, if you integrate this column from x naught to x, correct? Just integrate this column from x naught to x, dy by dx is equal to integral x naught to x fxy or you can write here t because it's dummy variable anyway. Then y of t and then dt because x appear here. Then if you apply your fundamental theorem of calculus, I get y of x minus y at x naught, which is nothing but your y naught, equal to this integral x naught to x f of t y t. Okay, I will get it. Clear? Or I can rewrite this as or yx equal to y naught plus x naught to x f of t yt dt. Okay? Can you write? Can you write? Yes. So let us call this is problem 2. Problem. Okay. This is called problem 2. Let us give this name to problem. Now I will give you very good exercise. Look at it. Exercise so that 1 and 2 are equivalent. What is the meaning of this? That we have to understand. What do we mean here? 1 and 2 are means what? If you can solve problem 1, that solution will be our solution of problem 2. If you can solve 2, that will be solution of. So 1 and 2 are both are same, you can see. However, you make a note. Is this a differential equation 2? Is it a differential equation? Is it a differential equation? Is it a differential equation? No. It is no more differential equation. It's an integral equation. Okay? It's an integral. So it's up to you whether you want to work with 1, which is differential equation, or you want to work with 2, which is an integral. So now we have seen 2 techniques: numerical differentiation and numerical integration. So if you like numerical integration, you must work with 2. If you like the numerical integration, you must work with 1. Okay? So 2 is no more a differential. So one part of the exercise I have proved because 1 I have proved. How do you go back to 1? What the idea? You differentiate this. You just differentiate, again use the fundamental theorem of calculus, you will get back this. You will get back. So this 1 and 2 are. It is clear? So it's up to me whether I want to work with 1 or 2. But it is very natural to work with 1, not with 2. Because that is our original problem is. We have just reformulate the problem. We just reformulate the problem. Okay, we'll do this both. We'll do the both. It is clear? So we have these 2 problems and let us understand. So first, what do we mean by a numerical solution? That we have to understand. Okay? What is numerical solution? What is the meaning of numerical solution? Like what do you mean by a solution of this? You are looking a function y of x. You are looking a function of y of x. Like if you have d over del to y and y is equal to 1, what your solution is? Y equal to exponential x. Right? Exponential x. And that function has to be differentiable, otherwise it won't satisfy. So you are looking for a differential function which satisfies. Then what do you mean by a numerical solution? If you say numerical solution, I cannot think of a function of x. I cannot think of a function of x. It has no meaning. That means you are looking for a discrete solution. You are looking for a discrete means what? At some point you can find the solution. At some point you can find the solution. So idea is, so numerical solution means what? We will find, we find solution at a point. At a point. At a point. Understand? Okay. So how do you do that? So idea is, first you have to discretize the interval because you want to have a point, correct? So that means the point should be of the interval of that. You have to discretize the interval. Right. So you have, how do I do that? It's up to you. You have your A, you have your B. Okay, you have your A, you have here. So let me say this is x0. Next point is x1. Next is x2, etc. Keep on doing this. So how do I discretize it? How do you do that? So first, if it is better, decide your h. How do? So let's say h is my b minus a by n. Okay, h is b minus a by. It will give you the uniform partition. It will give you the uniform. It will give you that. Otherwise, you can always do that. Something. Yes. Like this. Also, you can do this. So if you take this h equal b minus a by n, then my points are given by x0 plus ih. My points are given by x is equal to x0 plus ih. X0, you know what is that? What is that in this case? A. Right? The interval given to you know x0. That means you know all the points. So we have discretized the interval, which is you seems to be easy, correct? But that is the most difficult part in numerical analysis. That is the most difficult part is how do I discretize the given interval. That is the most difficult part of the numerical analysis. Where you have seen it very easy. We will come back. How it is very difficult. Okay. Now I have the points. So let me write this again. You have uniform point or equally spaced point. Okay. This is my x0. This is my x1, x2, x. But the last point would be x. Okay, these are my points are. Now what next? What next? Now you have to discretize your given problem, either 1 or 2. Either 1 or 2. And then find the. Okay. So let us get the idea from here. Get the idea from here. So I want to approximate. So recall, I will write few formulas here. Okay. If you have, let me write down integral a to b fx dx. I can also write this is b minus a into f of a. This is approximation, okay? And we have trapezoid rule is a to b fx dx as b minus a by 2 into, tell me, f at a plus f at b. Correct? We have seen it? Yes? We have one more, Simpson 1 by 3rd. Okay? We have many. What is that? b minus a by 6 into f at a plus 4 times f at midpoint a plus b by 2 plus fb. Correct? Let's say we have this. Now I am going to work with problem 2 because I am going for numerical integration. Okay? Then we will go with numerical differences. And you will see finally output is same, we get the same answer. Okay, of course. So how do I use this integral to in mind it? Here we have x, here we have x. Okay? So we'll come back to this. So now I can read this is true for any x, so this is true for x1 also, correct? So I can write y x1 equal to y naught x naught x1 f t y t dt. Okay. Now look at it. I can apply any numerical method which I want here, like 1 by 3rd, 3 by 8 or many of those quadratic formula. The problem is this I do not know. Do you know this? y of t? Do you know? We don't know. So our problem is we want to find actually. We do not know this. The basic problem in this case is we do not know y of t. Otherwise, I would have applied any method which I want and get my y of x. The problem is I do not know y of t. This is a big problem. But if we apply this, let's say apply even quadrature first. So then we get. So that will put my notation like just this notation. y1 means y at x1, or that means yi is nothing but y at xi. Okay, these are notations are very precise. We give yi nothing but y at x. The points which we have here. Understand the point which we have? Then I can write y1 is equal to y2. You want to apply this quadrature here, right? That means I cannot write equal to here. Understand? I cannot write equal because this is some approximation. This is some approximation. Then what the formula is? B minus A. That means x1 minus x0. What is x1 minus x0 is? H. Correct. H. Value at the initial point at A. So what is A here? x0. That means you have here x0 y. Is clear? Yes. So y1, it is just an approximation like this. Now I will write a numerical scheme. See, in any scheme, you cannot have approximately equal, correct? You must have equal only, then only you can solve. Understand? Otherwise, you cannot solve. In my textbook, they always write equal to here, many. They write equal to here after that. But it's completely wrong. This is wrong because this is an approximation. I cannot write equal to. Now, my numerical scheme is, I will write here W1. So, W1 I define equal to W0 plus H F F0, where I have my notation Wi is nothing but F at W at xi, and this is my numerical solution at x equal to x. So my exact solution I am denoting by y. My exact solution is I am denoting by y. Numerical solution I am denoting by w. It's again a solution at some point. It's again a solution at some point. See, this is my initial point, correct? So what should my w node? I must make use of what is given to me. So, okay, where this w node is equal to y, which is given to you. It's a point, correct? Which is given to you in the equation itself. This is my, and hence I have the scheme. So see, if you know your w node which is given to y node, I can compute the w1, correct? I can compute the. So again, let us have this. You have these points, okay? You have here x naught, you have here x1 and x2. Idea is simple. So using this value I will find here, correct? Now can I find the value here using this also? Can I find the solution at x2? Yes, you write W2 now, okay? So I will write my scheme is, now this is my scheme. Wi plus 1 is equal to Wi plus H F xi w. I goes from 0, 1 to n. Suppose you want the solution here, correct? So you have to vary this I up to where you want. So I want at 2. I want solution at x2. So you should stop it here. You should stop it. You understand? You must stop it here and get the. So that's what your famous Euler scheme is. Euler is given by Euler. You see, we have not done nothing, correct? We have not done anything. This is what the Euler This simple application. Can you increase volume? Battery is low, or my battery is low. Okay, so this is what your famous Euler scheme is. It is clear? Now suppose you will go with this quadrature a to b fx dx, and what scheme we get. That's it. Is this clear to all of you? So if you go with this quadrature number 2 with using what a trapezoidal rule, what happens? So in this case, let me write down this one formula. This is 2, this is 3. So this what we have done with 1. With this 1. If you proceed with 2, then what happens? You will see. So that means I will write y1 approximately to y0 plus. What it says? b minus a by 2, x1 minus x0 by 2. That means h by 2. Okay? H by 2. Value at fa, value at this point. That means your fx0, y0. Value at x. See, t is a y of t. So if you put here x0, that means you have f of x0, y x0 is y0, plus value at b means you have fx1 and y1. Correct? Yes. Now if you want to write your scheme, how to write it? I will write here w1 equal to w0 h by 2 f of x0 w0 plus f of x1 w0. Okay? But here we have some problem. What is the problem here? See, you want to find w1, correct? But this w1 appears here also. This w1 appears here also. We don't have such a scheme like w1 equal to w0 plus like this. Understand? We don't have such a scheme. Then what I do? So here we have two ways. One way is I can, because you know your f, correct? I can think of this is a equation in w. This is an equation in w. This is an equation in w. And using your root finding techniques like Newton method, whatever bisection method, I can find the w. This is the root of this, correct? I can find the w. Using your root finding, there is nothing but now a root finding problem. This is nothing but a root finding. But if we go with this, then we have to start initial gate. We have to do so many things, right? We have to do so many. So we will not go this way. We will not go this way. Another way is, why don't you use W1 here? So let me write this Z1, okay? I will write this is Z1. You can change, okay? Z1. Because this is unknown. Where this Z1 is, I have computed like this, correct? Z1 is, you can say W0 or F of X0 W. Okay? This is my. Now I know my Z1, correct? Do I know my W0 which is Y0? H. Oh, H is missing, correct? It is just to motivate. Okay? This is what my. Now, correct? Now I can write my scheme. Wi plus 1 is the same fact, which I will show you. Now I can write my scheme Wi plus 1, etc. And this is called Euler modified scheme. Euler modified. Okay? Since I have some approximate which is unknown to me, I have this. Correct? It is clear? Now let us go with the third one, and you will see why I said this problem, working with problem 1 is more natural than problem 2. You will see why this is more natural. So if you go with 3, tell me what happens. Okay, if you go with 3, then you don't have to copy anything, everything in the slides. You don't have to copy, correct? Everything is in the slides. Okay. So if you do that, I will approximate this by y naught plus. Tell me. You have here b minus a by 6. That means you have here h by 6. Okay. Simpson 1 by third rule. H by 6. Then what we have? F of a. F of a means f x naught y naught, correct? Plus 4 times at midpoint a plus b by 2. A plus b by 2. So I will write this as 4 midpoint, that means the f of x half. This is the midpoint of x naught x1 plus. So x half is precisely your x naught plus x1 by 2, because it is a midpoint, correct? Then corresponding I will write solution y half. Y half, correct? Because x plus you have f at x. Okay? This what we can write. So what we are corresponding scheme is, the scheme is you replace this y by w. You replace this y by w. And then you can write same fashion. But here I have to suppose write the scheme as w1 is equal to w naught plus h by 6 f of x naught w naught plus 4 f x half w half plus f x1. Okay? Yes? So like previously we have problem with w1 that we have sorted out, correct? But here we do not know w half also. Do we know? No, we don't know. So, but if you use some suitable approximation of w half and w1, some suitable approximation, then we can have a scheme which is called Bangyakutta. Okay, that we'll see later. But that's the thing. If you proceed in this fashion, we had so many problems. We had so many because we don't know w half, we don't know w1. Similarly, if you go Simpson's 3 by 8 rule, you will have 3 unknowns. You have 3 unknowns which I do not know. So that is the problem with if you proceed with numerical integration. That is that. It's clear? Okay. Now what the other technique is? Now we have to go with numerical differentiation. We have to go with numerical differentiation. That means we are solving our original problem. So what the idea there? Use the Taylor series. We use the Taylor series to approximate the okay, how to do it. It is clear? Everything is right. Don't worry. What I am asking you, everything written nicely in the slides. I will show you. Okay? Now let us go back to your original problem is okay. You have dy by dx is equal to f of xy, where x belongs to some interval ab and y at x naught is y. Correct? Now we will go with here. Now we will approximate the derivative. Now we will approximate the derivative. That's right. Now we will approximate the. So I told you to approximate derivative, you can go with Taylor series, or if you are you don't have the function or give Taylor form, then you can fit a polynomial and then differentiate that polynomial. But here we know the y, correct? So I can go with the Taylor series. So write down the Taylor series. Okay. So what is Taylor series? So I can write the Taylor series y at any point. Let me take the point xi. This is given as yi. What is yi means? What is the meaning of this? y at xi, correct? Y at x plus, tell me, x minus xi, x minus xi, x minus xi. Then we have y I dash, one derivative, correct? Plus we have x minus xi square divided by factorial 2. Tell me fast. Then you will appreciate this. You have yi double dash. Keep on doing this. Somewhere I will have x minus xi and divide by factorial n. Okay. Then y n plus. This is my like a polynomial plus the error part. What is error part is here? X minus xi is to power n plus 1 divided by factorial n into yi not I, n plus 1 at some point xi. So xi is lie between xi to x in some point. We do not know xi and hence we don't know that. So but I can always write. I can always write. I told you this is true for any n. This is true for any n. You fix your n, you can have. Suppose I will take n equal to 1, then what happens? So we have, so n equal to 1, what we have? Let us understand. We have y and x equal to, this is equal, correct? yi plus x minus xi, yi dash plus n equal to 1. This will be your error term. This will be your error term, correct? So I have x minus xi square divided by factorial 2 yi double dash not at xi, correct? It's clear? It is clear? If n equal to 1, n equal to 1. So this is my error term is correct. This is my error term and it has a fact. It's clear? This is true for any x. This is true for any x. So I can write in place of x, xi plus 1. So I can write this as yi plus 1, yi plus xi plus 1 minus xi. What is the number is? Always h. Xi plus 1 minus xi is always h. So I write here h into yi dash plus. This is the error term. What is that? You got h square by factorial 2 y double dash. Is this clear? Is this tab is clear? Now this is error term, you don't want that error term. Suppose you don't want. That means what? This will be never equal. This will be approximately equal. Correct? So I will write this as yi plus 1 is approximately equal to yi plus h. What is this number? Yi dash is nothing but f of xi y. So I have here f of xi plus I am not writing the error term. That means you can write. Correct? Now I will write my scheme. What my scheme is? Tell me. Replace this y by w. Replace this y by w. And this inequality becomes equal. So we have wi plus 1 is equal to wi plus h fxi. Correct? This is what your again Euler scheme is. Euler. Correct? I got back my Euler scheme even though I go with numerical. It is clear? Now suppose you take n equal to 2 and what problem we face? That one. Okay. If you take n equal to 2, what we have? Okay. If you take n equal to 2, so you have tried same steps. That means this will be your yi dash plus third derivative will be having the third derivative will be error term. Correct? So can you tell me my scheme directly? My scheme should be like this. Wi plus 1 equal to, okay, Wi plus h fxi, or let me just tell you otherwise you will get confused. So let us write down with y. So you have yi plus 1 is equal to yi plus x minus xi means h yi dash plus h square by 2, and this is your y I double dash, okay, plus now you have the error term. Now you have the error term. That nothing but h cube by 3 factorial 3 and y triple dash j. Correct? If n equal to 2. Now, if you remove this error term, okay, remove. You can write yi plus 1 approximately equal to yi plus till here, correct? Okay. Now, if you write scheme, what happened? You understand? You have yi plus h. Here I can replace this xi yi w1. Like previously, correct? What should I do with this term? Here you have double derivative yi double dash. I do not know. Do you know? I do not know. Okay. So this is nothing but actually, if you look at d over dx of fxy, correct? What is the meaning of this? If you take double derivative of this, you have to take derivative of f also. You have to take derivative of f also. Okay. And which is related to x equal to x. Yes. Only problems comes this. Or that made a w. How do I differentiate? So question is, what is the meaning of d by dx of fxy? That's all you have to answer, correct? Because here this yi double dash is nothing but d by dx of fxy at the point x equal to. That's the meaning. That's the meaning. How do I compute this? Clear? So how do I do this? Come on, tell me fast. How do I do this? Yes? Any? See, y is a function of x alone. So finally this will be a function of x only. That's why d by dx makes sense. Here y is not independent variable, correct? It's not function of two variables like f of xy. Then you can write d by dx. Now write del by del x. How do I compute this? Right, this by chain rule. So 12 by 2x plus yeah 2f by dou y into dy by dx. This is by your f is a function of two variables x and y, correct? Like this. So now your answer would be here. This is your del f by del x plus del f by del y into what is this? F. I know this f of x, correct? This is how you can compute the derivative. This is how you have compute the derivative, correct? And the meaning of this is understood in this sense. The meaning of this understood in this. It is clear? Is it clear? Similarly, I can go for n equal to 3 and n equal to 4, etc. Yes? So if you take n equal to 1, you get the Euler method. If you take n equal to 2, you get this scheme. This is called scalar series of order 2. Scalar series of order 2. If you go n equal to 3, you get scalar series of order 3. If you take scalar series of order 4, it's called n equal to 4, this is scalar series of order. Now, if you understand which one is better, how do I explain? Very quickly. No theoretical. Which one is better? We have taken equal to 1, 2, 3, 4. Out of 4, which is scheme seems to be better? Look at. If you have n equal to 1, we have this like h square by 2, desired part, correct? If you take n equal to 2, we have here h cube. And h is a small number, correct? So our ideal when h tends to 0, this must tends to 0. So look at this going fast, h cube by 3, correct? Compared to h square by 2. And if you take n equal to 3, you get h4 by factorial 4. You understand? So if you increase your n, you have a faster conversion. You have a faster conversion. Because this error term include your h. So error term, if you have more power of h, that would be fast by default. That would be fast. Correct? But so that means I can make this Take n equal to 100. Take n equal to 100. Correct? Then my answer will be having h raised to power 101. Very fast. But what is the problem? We have two problems. First of all, your y should be that smooth. Correct? I can make use of this provided your solution is that smooth. Provided solution is that smooth. Otherwise, I cannot make use of it. Correct? The second problem is you have to compute this derivative. You have to compute this derivative. Okay? You have to compute this, which is very difficult. Which is very. So to avoid this computation of derivative, the Range-Kutta method. So there are two mathematicians, Range and Kutta. They work on this and get two different schemes, Range-Kutta 2 and RK. So Range-Kutta 2 is based on n equal to 2. Only idea will avoid this computation of this derivative, and this will lead to RK2. For n equal to 4, you have the RK4 scheme. RK4 scheme based on the Taylor series of order 4, you get the RK4. The most famous scheme is RK4 program. This is very good. RK. Okay, is this clear? So let us go with slide now. Go next. Go. This way I have explanation. Okay. Yes. Go. Go. Next. So this is what your I have told you your IRL scheme, modified IRL scheme is. You have get ZI plus 1. This can be computed with the help of this W. So you can think of this is my IRL scheme, that is modified IRL scheme. This is a combination of these two. In some sense, we say first to practice solution, then correct the solution. I will not do it. Okay, this is my IRL modified scheme. Next. Okay. Now we go back to our numerical integration with Simpson 1/3 rule. We have to have x half and y half. So if you take some suitable approximation of y half, you will get this scheme. So wy plus 1 is wy plus some constants m1, m2, m3, m4, which is computed by this. Wait. So what is m1 here? H, f, x, I, w. m2 is this and m3 is this. You plug this here to get the. This is the famous RK4 scheme. So it has two ways of deriving. One way is you go with numerical integration, have a suitable approximation of y half to get the scheme. Another way is to go with Taylor series expansion up to n equal to 4, correct? And then you get this. So in your syllabus we have only 3 schemes. Euler method, okay? Euler modified method, and this RK4. We will do the computation. Is it clear? We will do the computation. Next. This is your, I showed you RK2 method. RK2, which is based on n equal to 2. So what the idea? Wy plus 1 can be written in this form. So only thing, this is unknown, correct? This is by unknown. It's just like your modified RN scheme. You have here some unknown. This can be given by this part your RK. One thing actually you have to remember this formula, because you cannot drive it. It's very difficult to drive. You have to remember this formula. Okay. This is why I told Taylor series expansion, correct? Yes. Okay. Yes. So see, for n equal to 1 we get your Euler scheme. For n equal to 2, this is the scheme over here. For n equal to 3 we have this. For n equal to 4 we have this. So in RK4 method, yeah, you have to avoid this derivative. You have to avoid this derivative, and it's a big proof. It's a big. So let us solve one problem. Take this problem. Write down, everyone. Then I will show you the MATLAB code. If you understand one problem, then you can compute yourself, correct? Let us do. With every method we will do. I will do here. output.